Hey everyone, and welcome. Today we are diving deep into the language that runs our entire world. It's not English, it's not code like Python, it's something way more fundamental. It's binary, that simple, elegant system of zeros and ones that powers literally everything digital in your life. So let's pull back the curtain and see how this actually works.
But you know what? Before we even touch on computers, let's start with a question about us. Have you ever stopped to wonder why the number 10 is so, important? Our whole counting system is built around it. Why?
The answer is so simple, you've actually been carrying it around with you your entire life. It's our fingers. We use a base 10 system because for thousands of years, our 10 fingers were the original calculators. It's just baked into who we are.
Okay, now let's flip that. Imagine you're a computer. You don't have 10 fingers. You just have two. A switch that's on and a switch that's off. That's it. That's your whole world. So how on earth do you count anything with just two options?
So here's our game plan. First, we're going to explore this two-state world and why computers are limited to it. Then, we'll see how they actually count with nothing but zeros and ones. After that, we'll get our hands dirty and learn how to translate our numbers into their language and, just as important, how to translate them back. And finally, we'll connect all the dots and see why this ridiculously simple code is one of the most powerful ideas ever. All right, let's dive into that first part, the two-state world. Why do computers have to speak this totally different language in the first place? Well, at their very core, computers are made of billions of tiny little switches. Think of them like microscopic light switches. They can either be on, which lets electricity flow, or they can be off, which stops it. And that's all they can do. So we give those two states a name. We call on a 1 and off a 0. And that right there is the entire alphabet of computer language. Okay, so if your only letters are 0 and 1, how do you write the number 2? It turns out computers solve this problem the exact same way we do when we run out of fingers, or in our case, when we run out of digits. You just add another column. Just look at the pattern here. The column on the far right just flips back and forth. 0, 1, 0, 1, 0, 1. Easy enough. The column next to it flips half as often. 0, 0, 1, 1. And the one to its left flips even slower. It's a cascade. Think about what happens when we count to 9. We're out of digits, right? So we put a 1 in the tens column and reset the ones column to 0 to get 10. Binary does the exact same thing. After 1, it runs out of digits, so it puts a 1 in the next column over and resets the first one to 0. That's why the number 2 is written as 1, 0.
And just so you know the lingo, these positions have names. That digit on the right is called the least significant bit, or LSB, because it represents the smallest value, kind of like the ones place in our numbers. The digit all the way on the left is the most significant bit, or MSB, because it carries the most weight.
All right, now that we get the basic idea, let's make it real. How do we take a number we understand, say 26, and translate it into the computer's language of ones and zeros? There's a really cool method for this called successive division. Sounds kind of fancy, but all it really means is keep dividing by 2. You just take your number, divide it by 2, and pay close attention to the remainder. Then you take your answer and do it again, and again, until you get all the way down to 0. Let's walk through it with 26. Okay, first up, 26 divided by 2 is 13, with a remainder of 0. Let's hang on to that 0. Now we take the 13, divide that by 2, we get 6, with a remainder of 1. Cool, save that 1. Next, 6 divided by 2 is a clean 3, so the remainder is 0. Then, 3 divided by 2 is 1, with a remainder of 1. We're almost there. Finally, 1 divided by 2 is 0, with a remainder of 1. And since we've hit a quotient of 0, we're all done. Now for the big reveal. You take all those remainders we saved, and you just read them from the bottom up. So that gives us 1, 1, 0, 1, 0. And just like that, our number 26 is now 1110, 0 in binary. Pretty neat, right? So, that's how we can talk to a computer. But how does it talk back? Let's flip the script and turn that binary number 11010 back into a number that we can actually understand. This method is even more straightforward. It's called weighted multiplication. All we have to do is figure out what each position is worth, what its weight is, and then we just add up the values for all the positions that have a 1 in them. We can totally ignore the zeros. So for our number 111010, let's map it out. We always start from the right. That first spot is worth 1. The next spot is worth double that, so 2. Then double it again for 4, then 8, and finally 16. See the pattern? Each place is just double the one before it. Okay, now for the easy part. We just look for the ones. We have a 1 in the 16's place, a 1 in the 8's place, and a 1 in the 2's place. The others are zeros, so we ignore them. So what's 16 plus 8 plus 2? It's 26. We are right back where we started. It works perfectly. And there you have it, the two sides of the same coin. To go from our numbers to computer numbers, you use division. To go from the computer's numbers back to ours, you use multiplication. They're just perfect mirror images of each other. So we've gotten through all the how-tos. You now know the mechanics of binary. But that leaves the biggest question of all. Why should you care? Why does any of this matter? Well, it all comes back to that tiny on-off switch we talked about at the beginning, the transistor. Each one of those little switches is a physical binary digit. It's a bit, a single 1 or a single 0, made of real stuff. You could say it's the atom of our entire digital universe. And here's the thing that's truly hard to wrap your head around. A modern computer chip, like the one in your phone or laptop, doesn't just have a few of these. It has billions of them. Billions of microscopic switches, all flipping between on and off, thousands of times a second. So the next time you're scrolling through photos or watching a video, just take a second to remember what you're actually looking at. At its deepest, most fundamental level, it is nothing more than a mind-bogglingly long string of those simple ons and offs, ones and zeros. Think about that. Our entire complex, interconnected digital world is built on the simplest possible idea: yes or no, on or off, 1 or 0. It really makes you wonder, doesn't it? What's the next simple idea out there that's just waiting to change everything all over again?